I've cheated and I've lied.
So I took this doubling every year and extrapolated it 10 years from 1965 to 1975 from 60 components to 60,000 components on a chip.
First thing you have to tell him is, guys, we've been giving you a free ride for 30 years while you write your crummy software and we made it faster. Right? That's over.
The future is parallel. Single cores are not getting any faster.
Well, good afternoon. Welcome to CSE141 again. I'm Professor Usaki. Today we are going to talk about instruction set architecture. Before the lecture, we usually would like to play some music, and today we played a music called One Thing Right. You know, most of the time in our life, we did a lot of things that doesn't lead to the consequences that we want. So that's why sometimes we feel like we're not doing the right thing, right? Yep.
What you texted me where there was like little sums were.
What? Hello. So for today, we played a song before the lecture called One Thing Right. So so what I want to say is that welcome to this class, and if you are staying, I believe you are doing one thing right. And we are going to tell you a lot of good things about computer architecture, and that will be probably the most helpful for the rest of your life. So today we are going to start talking about the first topic in computer architecture, that is instruction set architecture. But before we start, there is a very important concept that we bring up in the last lecture, and I do want you guys to remember that thing is called von Neumann architecture. So every modern computer is right now implementing a von Neumann computer, and what's the idea of von Neumann computer is that your computer has two main components called processor and memory. But you know, memory technologies right now we have like DRAM, they are not non-volatile. So if you compile the program, you don't want it to vanish, then the only thing you can do is that you need a secondary storage. So although the original flavor of the von Neumann architecture doesn't include a storage, but storage is actually very, very important, because without that, there's no way you can keep those results. You can keep your compiled program persistently. So that's why we need storage. And to execute a program in von Neumann architecture, you have to have the program first presented in the memory before you can start. And when I say a program, it includes the instructions and the data sets that the program requires. And when the processor needs to execute the program, first of all, it will go through the entry point instructions within the program. And usually there's a convention between the instruction set architecture and the processor, which we are going to talk about today. And starting from there, we are start running that program, and according to the content of the instruction, the processor will perform operations accordingly. Say if you have a processor, if you have an instruction that needs to fetch data from the memory, and that's the time you will get those data sets inside into your processor. And when the processor finishes an instruction, it would keep fetch the next instruction, or according to an instruction, if it tries to change the order of the program, then we are going to fetch instruction in a different direction. But that's basically the von Neumann architecture model. And the elegant part of the von Neumann architecture is that by loading different programs into memory, your computer can perform different functions. And no matter what kind of programming languages that you are using, it's always true that your underlying architecture is a von Neumann architecture. So even though you feel like I am interacting with C programming language most of the time, it's just because the compiler generate those machine code, generate those instructions, and translate your data into the desired format of the instruction set architecture. Then and then link together with other external library that you relies on. And when you need to run a program, it just follow the steps that we just mentioned in von Neumann architecture. Some of you saying that I have Java and the Java compiler compile the program not into the machine code, but into what's called by Java code and Java bytecode. And Java bytecode is nothing different. Is nothing well. So the Java bytecode is the instruction set architecture used by the Java virtual machine. And Java virtual machine is a virtualized von Neumann architecture as well. So when you need to run a Java program, you need to launch the Java virtual machine. And what the Java virtual machine that really do is that it will translate those Java virtual machine bytecode into the underlying machine instructions. And again, the translated code will be loaded into memory. The translated data will be mapped into the memory. The processor just do what exactly we have been doing as a von Neumann computer. And some of you are saying that I don't write Java, I don't write C programming language, so I don't need compiler. I use Python, I use Perl. And this interpreter-based language is still the same. The interpreter itself is a runtime compiler that translates your line of code, your code line by line into machine code, and then store the translated code into the main memory of your system. And it just do exactly the same as the rest of the operation of von Neumann computer. And in a previous lecture, we show a demo, and I saw some of you were murmuring in the chat saying that, oh, what about the data set scales up? So so I modified my program a little bit. So previously we have a fixed size of array. Oh, not this one, but okay, this one. Okay, previously we have a fixed size array, but right now I made it dynamically allocated. If we put another option, and then it will allocate a larger array for the stored data set. And remember what we said. If the option is 1, it will execute the sort, meaning that your program complexity will become order n log n. But if you don't do that, it's going to be just order n. So let's time it and see like how it performs. So let's start with not the order n algorithm, and let's try to scale up the data set a little bit. So let's say I have a million, right? So if I have a million items and then I have to initiate it, okay, so looks like it takes about 4 seconds to execute it with sorting, without sorting. But right now, what if I sort it first? It only takes half of the time, right? So okay, so let me now like having it 4 times larger, right? 4 million. So if I sort it, then the algorithm right now would take 8 seconds to execute, right? But if you don't sort it, right, how much time it will take? Let's wait. Let's wait. Let's wait. Let's wait. Let's wait. See, it takes very long time. It takes about 16 seconds, right? So now you should I hope I can convince you. Oops, what's that? Oops, where is the other slide? Oops. Okay, here we go. So I hope I can convince you that the complexity doesn't necessarily translate to performance, right? Complexity is lower doesn't mean the algorithm is faster, doesn't mean the algorithm is better on real computer. And there are tons of reasons behind that. And if you continue stay in the class, I will reveal the answers later. But right now, just stay tuned, pay attention. We will announce, we will tell you why later, and that's why you need to take this class. Okay, so hopefully that will give you some incentive to keep staying in the class. And in the lecture today, we are going to talk about the instructions. What's instruction set architecture, and an overview of MIPS instruction set architecture, which we are going to use throughout the textbook, and how to express a program in MIPS instruction set architecture. So before we start, we said this is a class that we are going to use the interactive teaching and learning method. And in the past, if we are in a class, I can do things like this, some group activities. But right now, because we are on Zoom, so the thing that I will be doing is that we will try to use breakout rooms in Zoom to have you guys discuss with people from the same residential colleges. So the process is still the same, but right now we just discuss it virtually. And you know, one thing I feel interested about UC San Diego is that we have 6 colleges, so it's something like Harry Potter. However, a lot of students after they are done with student housing, they just don't feel like I have any connection with the residential college. So hopefully this time through this class, you will get reconnected with friends that you met in the past. So for this, the first round, we will have you guys think individually. So for this question, please read it and submit your poll within 90 seconds. Once you have an answer, please submit through Zoom. Is there any issue of submitting it? I haven't seen anyone sending an answer yet. So it looks like the system has some issues with showing the poll on my screen. So let's wrap up in 5, 4, 3, 2, 1. Time is up. Okay, let me see. Well, for some reason, I still don't see anyone voting. So it's kind of odd, but I believe you guys must have something. So what if we just go to the breakout room discussion and, oh boy, and see what's going on there. So what we are going to do right now is that we are going to break up you guys into a few groups, and then we can do it. That's, oh shit. So let's go through this question again, discuss with your friends. Oh boy. Okay, so let's do the group discussion right now. All right, so well, so for some reason it's kind of interesting. It's kind of interesting that I don't see the poll is working today. So hopefully it will work later. But what if it looks like we have some issues, technical issues on Zoom this time. But right now, well, after the discussion, can I have someone raise your hand to tell me what do you think about the answer of this question? Like what, after discussion, what do you guys think? And tell me what do you think? Raise your hand, let me know. I will unmute you. Can someone raise your hand to tell me what do you think? Hello? Can I have someone? Okay, I have Shu Jing. What do you think?
I think it's 2. I'm not sure if I'm correct. So I think
did you get a chance to discuss with your friends?
Yeah, briefly, but we cannot see the option, so like we don't remember exactly which one.
Oh, I see. So they don't show that in the group discussion.
Oh no, it's like blank page.
Oh, really? Okay. So what do you think?
I think number 1 and number 4 is correct.
Okay, so you think many models of processor can support one instruction set architecture, and each processor manufacturer has its own instruction set architecture. So how about, so you don't think the second and the third, they are correct, right? So why is that?
Just cause like I feel like ISA is more like a language, like Java and C. Like it makes more sense. Like one kind of like instruction set can be used on different model, but like there can be multiple models supporting this set, and like 1 and 2 seems to be contradict to each other, and so does 3 and 4. That's why I think 1 and 4 is like more correct.
Okay, so but do you have some I would say some examples in real life?
No, like ARM architecture, like there's different version.
Yeah, there are different well, so okay, so let me tell you this, right? So who can manufacture ARM processor? Who manufactures ARM processors? Yeah, who can manufacture ARM processor? So okay, so
the same person developed the ARM instruction.
Okay, so say, are you a fan of Apple?
Kind of.
Okay, so what Apple recently said about what they want to do in future like development of their processors? Did they say anything about like in the future MacBook, what kind of processor are they going to use?
Are they using ARM?
They are using ARM, right? And your iPhone is using ARM, right? And who made the processor for Apple?
Like originally or?
No, like who made the processor right now for Apple?
Intel, right?
Yeah, but how about your iPhone?
I don't know that.
Okay, so Apple made its own processor, right? But Apple is not ARM, right? Did you see that? Right, so what does that mean? Many models of processor can support one instruction set architecture. Do you agree with that? Right, but ARM, Apple is like, okay, so AMD, well, let's say Apple is a processor manufacturer, but it doesn't have its own instruction set architecture. Instead, it has to use ARM, right? What does that tell you? So, okay, so let's look at some real life examples that we have. So if we have, if we look at the popular instruction set architecture we have in real life, there are 2 bit categories, x86 in ARM. So for x86 and also MIPS that we have in a textbook. And for x86, there are Intel and AMD, right? So 2 companies have the same instruction set architecture. For ARM, NVIDIA manufactures ARM processor. Apple has its own processor, ARM processor. Qualcomm has an ARM processor. Broadcom has an ARM processor. RISC-V a lot of people are making RISC-V processor. And for the MIPS instruction set architecture, well, there is not really a lot of them, but if you have, if you were an intensive gamer, you probably know, like Sony, they have their Emotion engine and the first generation of the PlayStation processor, all in MIPS architecture, right? So seeing this real example, right, is the first one correct? Many models of processor can support one instruction set architecture. Is that correct? Is that correct? Are you still there?
Yeah, I think it's correct.
It is correct, right? So now the second question that I want to ask, the second question, the second question that I would like to have is, well, the second thing, right? An instruction set architecture, is it unique to one model of processor? No, right? Because we see like Intel, AMD, they both have many processors supporting the same instruction set architecture, right? Do you ever see an example that we listed here, a processor support multiple, okay, Tui, question?
Yeah, I was hoping if you can explain or help like generally explain what does it mean that it doesn't have without interlocked pipeline stages? Like what does that mean?
Say again.
That's what MIPS is, right? So like I was reading, I just want to understand it.
Say again, what was your question?
You know, like MIPS, because it's talked about a lot in a textbook. I just want to like better understand the general idea of what it means to be like to not have pipeline stages.
Well, like, so that's too far away. So
okay,
instruction
I'm sorry.
set architecture is instruction set architecture. Your question will be answered later in the quarter. Is that okay?
Okay, I'm sorry.
Yep. Okay. Okay. So the second is incorrect, right? The instruction set architecture is not unique to one model processor. And we haven't seen an example of a processor support multiple instruction set architecture, and not every processor manufacturer has its own instruction set architecture. So the only thing that seems to be correct is the first one, right? Many processor models can support one instruction set architecture. So what exactly is an instruction set architecture? It's the contract between your hardware and software, and it provides an abstraction of the underlying processor. It tells you what the underlying processor would support in its like what kind of features this processor have for your software to use. And it also defines the memory space, because remember, right? What are the two important components in volume architecture? The processor and the memory. So the instruction set architecture is provide an abstraction that expose those volume architecture features to software to use. And programs are just a combination, combinations of these instructions. And the hardware implementations, we don't care. It could be directly a processor, and the processor, good or bad, depends on which one you choose. And you can use a virtual machine, you can use an emulator, and you can even use like, you know, TrendMonkey and with pen and paper to simulate those instructions. And when you are doing your homework, you probably feel like we are treating you guys like this, right? So this is the basic idea of instruction set architecture. So the instruction set architecture hide all the hardware details. It only exposes instructions which represent the functions, the features that your hardware supports to the software. However, we allow the programmer to completely ignore what's in the underlying architecture. So the abstraction looks like, okay, let's say Intel Core i7 and AMD Ryzen, they both support x86 instruction set architecture. But when you are writing your program, you are writing your program on top of these abstractions. So all you see is like this, we have an x86 processor. And for Ryzen, it's still an x86 processor. So there is no difference between these two. This is the power of abstraction. So on the other hand, if you feel like this is still too hard to understand, that's the example I have. Like yesterday, we talked about these two Pokemons, Pikachu and Mimic, right? So, well, if you don't want to spend time to dig into the detail of these two Pokemons, then the only thing that you need to know is that the game itself present an abstraction, right? All you need to do is that if you press A, that's like the normal attack, and if if it's B, it's more powerful attack, and if you do X or Y, it's either jump or whatever, right? And it's the same for the Mimic, right? It doesn't matter what Pokemon you are using. If I press A, this is what it will be doing. If you press B, this is what it will be doing. Right, so that's the power of abstraction, right? So it helps us to ignore the detail of the hardware. But from this example of the game, you also know that if I want to write a program that better utilize the hardware, I should know how powerful is the hardware so that I can use the combination of their functions correctly, right? But that's a later topic that we will bring up in the class. So for assembly language, a lot of you have learned this in CSE 30. And the assembly language is a human readable representation of instructions and machine language. It's a direct mapping between the operations that are supported by the underlying processor. So it's just a human readable representation of those zeros and ones representing the instruction set architecture functions. So let's say, like, if you have a strings of zeros and ones like this, and we said this is a MIPS 32-bit instruction, you can directly translate it back to an assembly instruction like this. It's an add instruction, add B0, A1, A2, right? Okay, so now let's talk about but in the rest of the class, I don't want to torture you guys by decoding those zeros and ones. So we are assuming that we are, when we say assembly language, we use this to write instructions. It will internally be translated to zeros and ones. And for the class, we don't want you to worry about the translation. So let's say for an instruction in instruction set architecture, or say in general in instruction set architecture, what do we contain? So the instruction set architecture, as I said, is an abstraction of von Neumann architecture. So it must expose the feature of your processor as well as including like the processor operations and the memory. So it defines what type of operations your processor should support. So typically, a processor would support arithmetic, logic instructions, memory access instructions, control flow instructions that like branch or function codes. And it should also define like how many features this processor should support, how many operations this processor should support, and how do you align, how do you describe their operands and what type of operands, how big the operands that we support. And also the memory space, like another big part of a von Neumann architecture is the memory, right? Like how big the memory a program can use. So let's see, like if I have an instruction like y equal to a plus b, right? Then the operation is the plus, and a and b, they are the source operands, and target operands will be y. So that's a basic idea of instruction set architecture. And to express this one, you can either create an add operation, add instruction with 3 registers or 2 registers, depends on what your instruction architecture wants. And it's up to the programmer or the compiler to assemble your program into a combination of those instructions. So that's the basic idea of instruction set architecture. Okay, so I have 2 of you have questions. Debbie?
Oh, I just had a quick question. Are we going to be doing any coding in ARM or MIPS in this class?
So for this class, you will have, well, you don't have a physical coding. You don't have to physically coding it, but because the rest of the textbook, we will use MIPS instruction set architecture to explain. So in your assignment 1, there will be one problem asking you to translate the code by hand. Does that answer your question?
Yeah, thank you.
Okay. Who has, I saw another people raise your hand. Okay. If not, let's move forward. So let's give an overview of the MIPS instruction set architecture. So we said for a volume architecture, we have we are abstracting a processor, we are abstracting memory. So the process, so for the memory, the MIPS instruction set architecture is using byte addressing, and it allows the program to use up to 2 to the 32 bytes of memory. So you will have addresses starting from 0 to 2 to the 32 minus 1. And each of the address is a byte address. And within its processor, there is an implicit register called program counter, tells you where my program is at this point. And there's a set of general purpose registers allow you to store any desired 32-bit values. And its ALU exposes 50 operations, including add immediate, and immediate, or immediate exclusive, or immediate, and branch instructions. And to execute a program on this computer, you may have your processor has a contract with the with your memory controller saying that, okay, if I'm fetching an instruction, we will go to the program counter, and that is pointed by the current program, program counter in the processor, and we fetch that instruction from there. The processor will put it somewhere internally, and then according to the content of the instruction, saying that if right now you have a load instruction or a store instruction, it will examine what's the target address of that instruction, get that data into the register accordingly. So that's the basic idea of MIPS instruction set architecture and the abstracted MIPS machine. And for the MIPS instruction set architecture, all instructions are 32 bits. And we have 32-bit registers, and all registers, they will be treated the same, and numbered. The only odd register is the zeros register. So for the zeros register, it's always 0. If you write to it, it's 0. If you load from it, it's always 0. No matter what you do, it's always 0. So that's a special register. Other than that, the other 31 registers, they are general purpose, although there is a convention between your compiler and the machine architecture saying that you are supposed, see the sentence I put here. You are supposed to use these registers in this way. However, if you don't follow convention, you might create like error-prone programs, but it doesn't mean that the computer cannot work. So that's what it is about general purpose computers, general purpose registers, and they have 50 opcodes, meaning that they physically support 50 different types of instructions, and they have 3 different instruction formats: the R-type instruction, which is a type of instruction that all operands are registered, and I-type instruction, it's called I-type because one of the operands is an immediate value. And there is also J-type instruction because it's non-conditional, non-relatively branched. So it's basically a jump. So that's why it's called J-type instruction. So these are the 3 basic types of instructions in MIPS instruction set architecture. So for this class, this is just the subset of MIPS instructions that you will be using most frequently. And the usage of this instruction is right here. Like for the add instruction, if I'm adding S1, S3, S3, S2, S3, it means S1 equal to S2 plus S3. So the target is the first operand. However, and there are only two. If you want to access memory, only two categories of instructions that are allowing you to do that. That is the load instruction and the store instruction. However, for the store instruction, sorry, I have a typo here. For the store instruction, this one is the source, not a target, because for store, you are moving the content from the register to a memory address. So that's why this register is the source instead of the target. So that's the only instruction in MIPS instruction set architecture. The first argument, or say the first operand, represent a source. So this is the overview of the most frequently used MIPS instructions. So for R-type instructions, its encoding is like this. And as I said, the common thing about R-type instruction is that all the registers, they are all the operands, they are registers. And the encoding, the detail of this instruction, we will leave it to the lab. And for I-type instruction, as I said, they have an immediate value, and the immediate value is only allowing to be 16 bits. So if you have a value that you want to assign as a constant to a register, and it's more than 16 bits, you can imagine you probably have to use I-type instructions twice to make it happen. And also, for load store instructions, they belongs to I-type instruction, which means that they allow two registers as their operands and one immediate value, which we call offset here, as their arguments. So there is no load word instructions like this, because for this one, it has 3 registers as its operands, which is not an I-type instructions, and there is no R-type load store instructions. So that's not allowed in MIPS. If you really want to do this, you have to separate them into you have to separate this into 2 instructions. So this one is not allowed. Just want to make clear, because I saw a lot of people previously in their homework, they will do that, but that's not allowed. And this is load store, and generically, data transfer instruction like load store, they are the only instructions that could access memory. And within its second argument, we usually encode the second argument like this. So this is called the base register, and this is called the offset. So the address of the memory that you are going to access is actually the content in S0 plus 8. So let's say if your S0 right now is, let's say like 0000F, well, not F, say 00C, right? And if you are familiar with hex, you know like C represent 12, right? So if I said I want to access an address of 00C plus 8, it will be equivalent to the decimal 20, or say in hexadecimal 14. So that's how you get your memory address in data transfer instructions. So data transfer instructions, they are very, 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 very important. So so I want you, and knowing the memory abstraction is also important for the rest of the class. So right now, I want to encourage you guys to look over this question and tell me what do you guys think? Okay, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, so for some reason, let me see. Because I have a hard time seeing what's going on in the poll. So, okay, so for this question, I have 74% of you think the answer is A. So it seems like a majority of you think it's A. So why don't we just have someone raise your hand and tell me why the answer is A instead of something else? Raise your hand, raise your hand. Okay, I have tweet. Okay, what do you think?
I just followed the textbook. They did an example where they basically take 5 and just multiply by 4. And
Okay, but
also
why
give you the
multiply by
starting
4? Why
because
multiply by 4?
every
Yeah.
word is 4 bytes.
Okay,
And
but that's a word, right? And why integer is a word?
because word doesn't just mean word, it means like 32 bits or 4 bytes. It's a unit of measurement. And integer is also a word.
Okay, integer is exactly the same width as a word in MIPS instruction set architecture, and a word is 4 bytes, right?
Yes.
So if you are accessing the 5th element, then you should be visiting the base address plus 4. And because the offset in this instruction is 0, so so it means that the outcome of T0 T0 plus 0 must be the target address, right? And if the target address needs to be this, then this is going to be the answer. Okay, so I'm glad that most of you get it right, and hopefully the explanation would clarify some of you have some misunderstanding about the memory addressing in MIPS instruction set architecture. So right now I'm going to and continue our introduction on this different types of these instructions in MIPS. So there is I-type, another I-type, there are also other instructions, I-type instructions like branch instructions, and like branch equal, it means like I compare if both of them are the same. If they are the same, then I set a PC to be something like this, right? So that's the definition of the branch instruction. But as you can see, because it has an immediate field, so it's an I-type instruction. And for the J-type instruction, it's non-relatively non-branch jump. So it encodes an immediate field, but what it really do is that we just go to the value pointed by the immediate field. So there are a few J-type instructions that we will be using, and especially useful when we are doing function call. For example, if you want to call a function in MIPS instruction set architecture, you will use jump and link. So for the jump and link instructions, you give the program counter of a function, for example, like quick sort, and it will set your, it will first restore your current PC plus 4 to the return address. And the reason why here we have to plus 4 is because later on, you will know there is another instruction called return. When it returns, it goes to the content in R31, or say the register RA. So if you don't plus 4, what would happen is that you will keep going back to the jump and link instructions, and you will jump and link instruction, and you will never be able to move forward. So you have to do TC plus 4. And the reason why we have to plus 4, because in MIPS instruction set architecture, as we said, every instruction is 32-bit wide, so they are exactly 4 bytes. Okay, Byron, question?
Yeah, how do we know that, like, when we pass in like quicksort, how do we know that it can fit, the address can fit within 26 bits?
Okay, that's a good question. So the answer is that the compiler compiles the machine code, right? So it knows if the program is big enough or not. And they must be, the compiler must deal with that. And the programmer knows there's a limitation of 26 bits. So it's our call.
Oh, okay, I see. Thank
Okay.
you.
So, okay, hopefully that's a good question. And then after we finish store the return address, we can finally set our PC to quick sort. So that's the JTAB instruction. So in your homework, you probably have to do something like this. So let me walk through an example like this. So if I want to translate a C code into assembly, MIPS assembly, this is what we will do, right? So this is the C code, right? So let's say if I want to translate the code, right? Think about that, right? First of all, for this program, what do we need to do, right? First of all, right? Initialization, right? Because we have the sum initialized at 0, the I must be initialized at 0. So let's get this ready, right? So that we need initialization. And the loop condition says that I must be smaller than 100. So you also need another thing to store 100. And then this initialization will help us to get the loop related variables done. But within the loop, what we need is load the content of AI from the memory to the register and sum it up, right? And the load, where to load, we have practiced in the previous question. And how to sum, there's an instruction called add to help us doing that. So and then finally, after we finish the lab, we have to increment the I by 1, right? So that's everything we need to do, right? So, and check if the I is still less than 100, right? So this is the basic concept of this piece of code. Let's see, by having these 5 concepts, how can we translate that into machine code? So assuming that integer is 32 bits, and we already have the base address of A array in S0, we have the sum in V0, and we use T0 to store I. So if I want to translate this pieces of code, as I said, I want to initialize the variable. So the first variable that we should initialize would be I. So and T0 stores I. So let's do AND instruction T0 with 0. And it will, and because 0 is always 0, so it helps us to initiate T0 as 0. And some of you may say that, well, can I use another way? For example, like, can I do add T0, 0, 0? That's also possible, and that's also good because because there is no unique translation between C code and assembly. As long as it gives you the right function, right result, we are fine with that. Okay, Byron, question?
Wouldn't it be dangerous to do the add because T0 is not, or like you don't know the value of T0
when I
before?
When I say add, I'm saying like if you want to use add, it will be add T0, 0, 0.
Oh, 0, 0, sorry. Yeah.
Yep. Okay. All right. So after you finish initializing the I, again, right, you can initialize the 100, right? And for 100, because there is no register code 100, so we have to use the immediate field. So in this way, instead of using the conventional add, you have to use add immediate. So it turns out that we are doing add immediate T1, 0, 100. Okay, and right now, I am doing the load directly. But why am I doing this? Why am I doing this? Because here I am, well, think about this, right? Because I initialized the I to 0, and I must be smaller than 100. So the first iteration will definitely go. So there you don't, because you already know I is 0. 0 is smaller than 100. So the first comparison between I and 100 that could be ignored to reduce the amount of instructions we need. So that's why here we directly go into the load to perform the second test, load A0 into the register. So S0 stores the base address of A0. So S0 plus 0 will give you the address of A0 and load it into register T3. And then, because right now T3 has the content and sum is right now in V0. So you just add V0 with T3 and put it into V0 again as sum plus equal to 10.1. So these two lines of code would help us to finish the sum operation, the statement. And right now, the next line I would put is that I am going to move, I'm going to do the I++. However, it seems like we have I++, but if you want a code to be really efficient, why don't we just directly move to the next item in the A array? And as we previously mentioned, right, the A array is an integer array. So each element is 4 bytes long. So what if we just add the address of S0 with 4? So S0 would move to, so right now you can think about S0 is a pointer. It will be pointing to A1 instead of A0 after we're doing this, right? So here we are we are advancing the pointer, and then we advance the value of I, perform a comparison. If it's smaller, so because we are incrementing, right? So if we are incrementing, if it starts with 0, if it hasn't reached 100 yet, it means that we are smaller than 100. So if the incremented value of T0 is not equal to T1, it means that the I must be smaller than 100. So in this case, we should go back to the beginning of the loop and remember the first instructions. The first instruction that stands for the iteration of the loop is actually in the load word instruction. So the loop should be here. So that's the whole idea of how we implemented the left-hand side code. You just need to use this following instructions and you are done. So that's how you translate C code into assembly. All right, question. Okay, I have Debbie, question.
Okay, so translating C into assembly, that's something that the compiler usually does, right?
Yeah.
So maybe this is out of the scope of the class, but I'm just like, can't really wrap my head around, like, isn't there like a lot of thinking that we need to do as we're like translating it? I feel like it's not entirely one-to-one.
Yeah, so here's the thing, right? But yeah, you have to, if you really want to create a very, very optimized code, you really need a lot of optimization algorithms to dig into the structure of the program. So that's why there's another class called CSE141, right?
Mm-hmm.
Okay.
Wait, so when it compiles by a compiler, it's not necessarily optimized?
It depends on your optimization level, yes or no. If you turn it on, it will optimize. If it doesn't turn it on, it will just do the very basic regular translation of the code.
I see. Thank you.
Okay. Other questions? Okay. If not, okay, Tweet.
Oh, I had a question for the loading. Like, what does it mean when you put the 0 in front and then parentheses the register?
So that's the convention of C programming language. So this means that the address of A0.
But then if you put the loop there, doesn't it mean it'll always get the address of A0 every time we go through the loop?
No, because we are advancing the value of A0 here.
Oh, so A0 doesn't mean anything. It just means like the current AI address. Okay.
Right.
Thank you.
Okay. All right, so hopefully this example would help you understand, figure out how to translate from a high-level language or any kind of language into machine code. And as I said, there are many ways to translate a C code, but efficiency may differ among translation. Some of you mentioned compiler optimization. That's really good because that's why we need good compilers, and that's why we need you guys to take a compiler class to generate highly efficient machine code. So, but before we move forward to another topic, I want to give you a few practice on MIPS instruction set architecture. So I am more convinced that we can move forward. So the first question that I have here is that, can you tell me for the code that we just translated, when we are executing it, how many instructions are actually executed? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so from what I can see from here, let me see. Okay, so most of you, wow, 78% of you think the answer is C. It looks like my answer is too simple. My question is probably too simple for you guys, or maybe all of you are getting wrong. So why don't we have someone standing up for the whole class to tell me why do you guys prefer C instead of other answers? Raise your hand. I need your voice. Okay, Twee, what do you think?
I'm not 100% confident, but based on the 5 lines that we'll have to keep repeating for the loop, I just multiply that by 100, and then I add the first 2 lines in the beginning.
Okay, that's exactly right. That's exactly right, right? So see, this is not the assembly, well, it's not really hard, right? So the loop will be executed 100 times. So just do it by 100 times and you will get the amount of instructions that are actually executed. So here I'm going to introduce another two terms. One is called static instructions. So when people refer to static instructions in compiler or in computer architecture, it means how many instructions are there in a compiled program, or say how many programs are there in your store, how many lines of code in your compiled program. So when you put the compiled program in a storage, that's actually when people are asking about like how big the size of your code is, it's actually asking you how many lines of static instructions do you have in your assembly, in your resulting compiled program. So in that sense, if people are asking about static instructions, the answer should be 7 because we have just 7 instructions. But for these questions, we are especially curious about how many operations while the processor is queued. So when you start running the program, this loop will be unrolled for 100 times, and the result will be the resulting number of instructions that your processor is queued will actually be 502. And that's called dynamic instructions. When your program is indeed in execution, it takes the amount of dynamic instructions to execute. But when you store it in the storage, in the memory, it takes the size of static instruction to store. So this is the definition, the distinction of these two terms. And hopefully this question would help you guys figure that out. So another question. Now, previously I translated the assembly languages for you guys. And right now, what if we have you try that? Okay, let's try to wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, so let me see. Here, oops, sorry. I think I have to. Okay. Okay, here we go. So, for this question, the answer is very diverse. I have 13% of you think the answer is A, 24% of you think the answer is B, 42% of you think is C, and 20% of you think is D. So, so from 0 to 3. So what if, but it seems like the idea of a breakout room doesn't work very well for today. So if possible, can I have some of you to tell me what do you think? So we can use that as a group discussion to replace the group discussion. Okay, I have Dan Ling.
Hello. So I think it's nothing correct because
Nothing correct? Okay, hold on. I saw someone else also raise your hand previously. Can you raise your hand again? Okay, so I have Byron, I have Twee. Okay, I'm going to unmute you three. So you guys will be doing the group discussion right now.
Oh God.
What do you guys think?
Okay.
Oh God.
Just discuss, right?
I don't think it can be any of I don't think it can be any of the three, or like things with 3 lines I'm a little bit suspicious of, because you need to first of all change values for return and n, but then you also need to check equality. And because we don't have a less than, like for, I don't know, I just don't think it's possible to do it in 3 lines. So I'm still trying to wrap my head through the third example, but that's just my thinking.
Okay.
yes.
So I think there's only one correct, but just like Byron, I'm still like trying to read through all the codes. But I thought 3 was the most correct looking one.
Okay, so let's look at the third one, right? You think 3 is the most correct looking one.
Yeah.
So for this piece of a code, we assume T0 has n, right? And V0 has return, right? So what this line is doing is what?
So that one is putting the value of 1 in a temporary register T1. Oh, but you don't know what is in T1 currently. So I guess
Yeah,
that's
so
incorrect.
this one probably doesn't work well, right? And
yeah.
Okay, this one doesn't work. How about so how about others? So why don't you think the first one looks well, Byron, why do you think the first one looks suspicious?
Because we haven't haven't covered the else statement. So if it's not equal to, then we don't set n equals to n minus 1. Oh wait, it already does that. Oh wait, never mind. It already does. Wait.
Right, so
because it already does that.
It compares it to 0.
Okay, so here's the thing, right? So here we did add immediate T0 minus 1, right? So we are doing n minus 1 here, right? So T0 right now has n minus 1, right? Here we are doing branch not equal. Branch not equal, right? Saying that if n minus 1 is equal to what? 0.
Yeah. Okay.
Right? We are asking if this is true, right? So if you move this one here, it's actually asking you if right now n is equal to 1. Right?
Yeah, so
you agree with that?
Yeah, and then it either changes red or
right. So if branch not equal, it tells you that it's not equal to 0. Right? What does that mean? It means that if it's not equal to 0, it means the n is not 1, right? So it should go to where?
L1. Or sorry, it'll wait, it'll still run L1
It should go somewhere else than L1, right? So this doesn't work, right? Because if you go to L1, it just add it just put 1 to it just put 1 to return, right? And for this one, I think if you it's the only difference between this one is that if it's 0, if it's equal to 1, then it go to L1. You will do the return. However, another thing to think about is that if it's not equal, according to the nature of MIPS instruction set architecture, it will go through. It will go through. right? So this is not right too, right? So this is not right either, right? Do you agree with that?
Yep.
So this one we know is not correct. How about this one? What's the difference between this one and?
It sets the return to n+1.
Right. So again, right, this one is not correct. So the right answer here is actually A. Nothing implements the desired result, right?
Yeah.
Do you all agree? Do you guys all agree with that?
Yeah.
Okay.
Jump.
Okay. All right. Thanks for you guys. And well, originally I thought that we can do this kind of discussion in the breakout room, but looks like the Zoom has some technical issues that I have to resolve. And right now, because I use the breakout Zoom for some reason, I don't even see the poll result from you guys. So I have to read it through my web interface, which is kind of not working very well for me. Okay, so but thanks a lot for your being patient today. But for this question, right, there is not really an answer here. Okay, so right now, identifying a bad question designed by your advisor, I believe you guys really get through the basic MIPS instruction set architecture. So another important thing that we have to mention, we have to support in an instruction set architecture is that, well, in software engineering or even in hardware design, we want to reuse your code, right? Like even Verilog you learned yesterday, right? We like to reuse things as much as possible. So we create modules in Verilog, and in programming language we create functions. So to support function calls in MIPS instruction set architecture, we have two instructions. They are jump and link, return. As I mentioned previously, for jump and link, it just helps us to set the program counter to where the first instruction of your function is, and it will store the caller address. And for jump and return, it just return your code to where the caller is. So this is the basic idea of these two instructions to help us accomplish the function call. However, if you look at what we need for a function call, it's actually more than that, right? Thinking about a function call, we need to pass arguments. And then the jump and link, as we just mentioned, it will help us to transfer the control to the callee. But in each of the functions, we also need local variables. And we also need to store return value somewhere before we can return to the caller, right? So these are the functions so the arguments, the local variable, the return value, we haven't talked about. Those two instructions does not really support. So in the next lecture, I will navigate into more detail about how the current MIPS instruction set architecture supports function call. But before you leave this lecture, there are several things that I really want to let you know. So first of all, this class, we have many different resources. And I know it's a bit of overhead for you. So let me list the resources that you have to track. So first of all, if you have questions, go through Piazza, and we will try our best to respond. But if you are posting it during the lecture time or some time that people are not awake, don't expect we respond you immediately. And if you want to turn in your assignment, if you want to perform reading quizzes, Canvas is the place. If you want to download the slides, if you want to preview the slides, if you want to see what are the questions, problems that we have in your homework assignment, check the website. And for the recorded video, recorded lectures, go through my YouTube channel. And if you have issues with Zoom, like what I have today, YouTube is also your friend. And for reading quizzes, I know, well, so first of all, thanks a lot. I see quite a few of you are trying to enroll in a class. So if you have enrollment issues so that you cannot access Canvas, I know there's an issue. So for that, I'm going to drop one more reading quizzes, and I'm going to split one big reading quiz into two. So I'm adding one more reading quiz, but drop one more now, right? So hopefully that would help us to compensate the loss of some of you. And if you still didn't see yourself get added into Canvas, I already contacted the IT support, but I'm not sure how much time they will address that. But if it's not done by tonight at 9:30, send me an email by 10. That's the time I usually try to get ready to sleep, and I will try to help you before that. Other than that, I have two of you have questions. Tui and Tui, what kind of question do what question do you have?
It's logistics. So I wanted you to verify the book version because I
It's
know
the fifth version of the computer organization. It's the link that you will see on the website.
Okay, that's what I have, and I checked on the website, but I just want to make a note, even though I already made it on Piazza, is that I think the reading quizzes for the hints, it gives.
Oh yeah, it's an older version.
Yeah, that's
and,
what I was gonna say.
Yeah, okay. Thank you.
Yeah, that's all.
All right, David, question?
Professor, that is not a question. That's actually an applause. I just wanted to say thank you for the lecture.
Okay, thank you. All right, and thank you all for attending this class, and I will see you tomorrow.